Thank you. Okay, so we're going to continue with our lecture on dark matter. Is my voice okay again today? I sometimes tend to mumble halfway through, so somebody raise your hand and say, okay, I'm speaking too softly. Okay, so just to recap, here's where we were last time. We are going to have 4 lectures. We are done with the first lecture, which was on evidence for dark matter and constraints on its properties. I want to remind you that if you haven't done so already, please do go ahead and look at these notes. They're a lot more detailed. How many people took a look at them? Okay, few. I think I would recommend, look, it'll be easier. The lecture will be easier to follow because inevitably they get a little bit more technical as things go on. So it'll be helpful to look at these notes if you haven't done so. And these, I will give an exam, that's true. There will be an exam at the end. And there are problems, there are small exercises in there. Some of them we've already done. Some of them you should do on your own. And they're quick exercises, they're not very long usually. Okay. So today's plan is that I'm going to tell you about growth of structure in dark matter. It will include a review of the matter power spectrum that has already been discussed. And depending on how much time we have, I will talk about how that matter power spectrum is different in different models of dark matter. So here is my goal for this talk. I hope that by the end of this talk, you will know what this plot right here is. This is a matter power spectrum, and you will have some ability to derive it from first principles. Time permitting, you will also understand while certain types of dark matter, particularly light dark matter, changes the shape of this power spectrum at small length scales or high K. So that's what I hope that you will get out of today's lecture. So if you don't get this out of today's lecture, let me know. By the way, there's a typo here. What did I do? Is this okay still? Okay. Okay, so there's a typo here. This should be k to the 4th. And you will know why it should be k to the 4th here. Okay. So the first part, it's going to be on slides because this is a review of what Rogerio has told you as well as what Julian has told you. I'm just going to review it quickly, partly because I think this is important. Yes. Partly because I think this is really important stuff, partly because I think it's really fun for me to do as well, so I will do it again even though they've done it. But I will take advantage of what they've done because they've really set up the problem well, and they've already explained some parts of it. The second reason is also I want to set up notation that I will use when I go to other models of dark matter so that you will see how to compare the two. So the first part that I'm presenting should be true of all models of dark matter. It's not specific to any model. The second part will be specific to some models. So let's start with this review. We're going to talk about this. Doesn't quite seem right. Should we change this? Let me try it one more time. Can we get rid of the screen somehow? Magic. Okay. So what I want to do is start with this review. So let me just quickly go through things. So we're going to be talking about a Friedmann-Lemaitre-Robertson-Walker metric, which is slightly perturbed. A is the scale factor, phi is the Newtonian potential, which is small, or generalized Newtonian potential that is small. Then we define a density contrast. This is a deviation of the density from homogeneity right here. This is delta. We define a peculiar velocity, that is deviation away from the Hubble flow. And I also defined a derivative d by dt, which is what is called a convective derivative. It's a derivative as you're moving with the fluid. Next, we write down our conservation equations. So the first equation is just a conservation of mass. Rogerio already introduced this. The second equation is just F equals ma. It's just Newton's law. It's telling you how acceleration is related to the gravitational force in this context. In GR, you just move this to the other side. This is part of the geodesic equation. So you can also think of this as momentum conservation. This is mass conservation. And the third part is your Poisson equation. This is just gravity. Okay, how is the gravitational potential influenced by fluctuations in density? By writing these equations, I've limited myself to sub-horizon scales. Okay, so scales that are smaller than the horizon. Otherwise, you have to modify these equations, at least in this sketch. Rogerio nicely told us that you can combine these three equations. If you combine these three equations, you get a very nice, simple equation for delta, the fractional density contrast, which is a nice second-order differential equation. It's simple enough that we can solve it. And when you solve it, some very elegant solutions come about. First, before I tell you about the solutions, this equation can either be thought of as being written in position space, where delta is a function of time and space, or because there are no gradients or no nonlinear terms, the same equation also holds if I think of delta in Fourier space. Okay. So both of this is fine. What are the solutions? The solutions are that if you are in radiation domination, then this pressureless fluid grows logarithmically. So the density contrast grows only logarithmically with time. However, if you are in the matter-dominated era, this is a part that has been talked about a lot, it grows as a scale factor, so it grows a lot faster. Notice I've changed from time to scale factor as my variable, just like sometimes you shift from time to redshift. I've just shifted from time to scale factor as my time variable. Something that Julian mentioned this morning, in this gauge, in this Newtonian gauge that you're working with, on superhorizon scales, this density contrast is a constant. Okay? It doesn't evolve. So if you set it up at some initial time, it remains the same as long as the modes are outside the horizon. So that I can't do in a Newtonian treatment, so I'm just adding it on. So what do you do with these solutions? You put them all together, and it gives you a way in which any density fluctuation evolves from being outside the horizon first to entering inside the horizon to evolving. This is the full solution. Let me, if I can, stop sharing here. I forgot how to go to, okay, let me just do this quickly. Even if it's not visible everywhere, it's okay. So what does this solution look like? So on the vertical axis, I'm going to put this delta A, this fractional density contrast in Fourier space. And for reasons that will be clear soon, I'm going to multiply it by k to the 3/2. Doesn't matter, I'm just care about the time dependence. And this axis here is scale factor. Let's draw it a little bit out because I will need it. Let's mark some important events in the history of our universe for this. The most important one is matter radiation equality. This is roughly scale factor is 1/3300 for this. And let's look at what the solution looks like. I'm going to draw something, and then we're going to discuss what does this represent. Okay. So here, the growth is logarithmic. Here, the growth is proportional to the scale factor. Okay. What do you think? Can anybody think about what this event here is? Yes. Sorry?
Yes.
I'll be done in 1 second, and then it's just a very quick one, okay. And then I'll come back. Can anybody think of what this event is? Why is this changing behavior? That's one possibility. What else can you think of? Horizon crossing. Okay, remember outside the horizon, modes are constant, they don't evolve. As soon as they enter the horizon, they started to evolve. So this is horizon crossing. So let's say this is for some mode with wave number k1. It enters the horizon, grows logarithmically, and then as soon as matter radiation equality happens, it starts growing linearly with the scale factor. Okay, so that's what's happening. Now tell me what's going on with this one. Sorry? It enters later. Where do you think it enters? Right here, right? So this is for the mode K2. So if it's outside the horizon, nothing happens. It's a slight lie, there's slight evolution, but for our purpose, it doesn't matter. It enters the horizon and then it starts evolving. If it enters after matter radiation equality, it enters and grows as a scale factor. If it enters before, it first grows logarithmically and then grows as a scale factor after equality. And the obvious important one is the one that just enters at matter radiation equality. And that would look like this. Okay, so they're all the same slope afterwards. Okay? And this is the behavior. If you want to figure out when a mode enters a horizon, what do? You say K equals A times H. This is what it means for the mode to be the same size as a horizon. And then you just say you solve for AK from this. So you pick a K value. Solving this equation will tell you when the mode enters a horizon. That's the way it works. Okay. So let me now go back. I'm going to close this. Okay. So is this okay, the screen? All right, so this is what this slightly complicated looking thing is. It's just what I drew right there. Now, if you're just interested in what happens, what is happening today, think about the following. You started out with the mode outside the horizon with some amplitude, whatever it was set up to be. It's that constant. Then, depending on when it enters the horizon, it evolves. If you just want to know what the amplitude of the mode is today, you plug A equals A naught, where A naught is 1, and you just ask what the solution is. And this is what it looks like. Okay, it has one part logarithmic plus the linear growth. The other part is just a linear growth, depending on when it enters. So we have the solution. Right? It was just based on the single equation. We know how these modes evolve. Different K modes evolve. And the distinction is just when they enter the horizon, before or after equality. As Julian and Rogerio have correctly said many times over, the initial conditions that are set up are, for our purposes, will take them to be set up by inflation. And Mehrdad will tell us a lot about it, but they're stochastic. We don't know exactly what the amplitude of each Fourier mode is. We don't have that information, right? We just have a realization of it, but our theory can predict something about the power spectrum, the statistical properties of this. So what I want to do is, here, this was a single mode with a definite amplitude. I want to convert this into a power spectrum. That is what we are going to put our information on top of, our observational information on top of. So you construct the two-point correlation function. This is how you define the power spectrum. And as Mehrdad will tell us, for the simplest models of inflation and what is consistent with observations, the power spectrum, the dimensionless power spectrum, which is k cubed times p delta, is roughly constant. It doesn't depend upon scale. So that's what it means to be scale invariant. Is this k cubed times p delta is roughly constant. 10 to the minus 9 is an observed thing. That's what we have found. You can write a k ns minus 1 to just to correct for slight scale dependence, but this is correct. So this tells you initial conditions. So imagine doing this expectation value on two of these guys on each side. Construct this together using this property of the power spectrum. And you are now able to translate our solution into a power spectrum. This is all a function of k because there's no time here, okay? Because I'm evaluating it today. But there's this AK sitting there. And to convert this AK, you have to make use of what I just said, that you make k equals to AH and solve for it. This will depend on when the mode is entering the horizon, before or after equality. And if you plug it in, you will get this shape of the spectrum. let's pause for a moment and just understand what it's saying. It's saying that for k greater than k equality, the spectrum goes logarithmically with k. For k less than k equality, it goes as k to the fourth. And we should rejoice at the fact that that's exactly what it should be. So just by this, what you've learned so far, you can now predict the shape of this power spectrum. It's k to the fourth here, and it's logarithmic here. Nothing else was needed. It was just that one equation with its solutions. Why am I also showing you this plot here? Because it's common not just to plot k cubed p delta, but sometimes people just plot, it's often people just plot p of delta. So you just divide this whole thing by k cubed. So now you get k and log of k divided by k cubed. Okay, so it's the same thing. We've just derived the shape of the matter power spectrum. Remember, the behavior was different depending on whether it entered before equality or after equality. So the characteristic scale where this peak is or where this bend is precisely the mode that enters a horizon at equality. So this is a characteristic scale that appears, and you should remember that it's about 10 to the minus 2 megaparsec inverse. K is 10 to the minus 2 megaparsec inverse. That's a mode that enters a horizon at matter radiation equality. Okay. Any questions about this so far? So this was kind of review, but my own sort of take on it a little bit. I think for those of you who haven't dealt with power spectra before, it's often, what does it all mean? One way of thinking about k cubed p delta is the variance of fluctuations on the scale k inverse. So that's another way of thinking about what this spectrum means. Okay. So k cubed p of k, you should think about as what is the variance, meaning deviation. You know, there's the mean, then you do standard deviation, and then the variance. It's the same variance. What is the variance of fluctuations on this scale L, length scale L, which is roughly k inverse? So it's a variance of fluctuations on a given scale. So that's what the meaning of this. That's why I typically like this power spectrum than the other one. Yeah.
How to represent the variation of the
density of dark matter, right? Or matter in general. Okay. So this is what it represents. So to give you some intuition, okay, where do you think? So if I want to know, this is a shape today. Is dark matter, based on this calculation, is dark matter more dense? There are more density fluctuations on small length scales or large length scales? What do you think from this curve? Small length scales, yeah? This is rising like this. Remember, large k is small lengths. So notice that there should be more fluctuations on small length scales compared to large ones. So that's what this curve is telling you. And this logarithm is important. It's not, you can't just completely ignore it, because if you didn't have this logarithm, you wouldn't get density fluctuations going above unity. You wouldn't have nonlinear structure starting in this way, right? So it's important. So you can't completely ignore the logarithm, although in first treatments, you can just put it flat and it's okay. Yeah? So in the first treatment, it's always good to just ignore this because it's simpler, but in detail, you should include the logarithm to see where it's coming from. Now, the reason I like talking about this is because when I myself was a graduate student, this was 10, 15 years ago, this was sort of the first calculation I did that I didn't understand from the textbooks. And I tried to figure it out myself, and I kind of did what I showed you right now. And I got the right answer, and that was the first time I felt like, oh, maybe I can actually do this stuff. Before that, I was like, I'm just reading what people are telling me, right? And so it was a good moment, so that's why I keep on wanting to share that. So it's a fun thing to do, and I think try to do it. Of course, you should develop your own way of doing it, not how I've told you to do it either. And it's a good way to learn this stuff, and it's an important curve. Let me now sort of give you a graphical way of understanding this power spectrum. Okay? So we start with, now what I'm going to show, this axis is wave number still. This axis is the amplitude of the power spectrum. And what I'm going to do when I run this movie is I'm going to show you the time evolution of this power spectrum from initial times till today. Okay? So I had just shown you the shape today, even though the solution, I could have done it for all times. Yes.
that K is the co-moving.
It's co-moving. K is co-moving K. Okay. So at early times, remember. So this is flat. Why? Can somebody remind me why is this flat? This is at very early times in the history of the universe. Sorry, it's out of. These are all out of the horizon at early times, and inflation has set them up to be roughly scale invariant. That's the initial condition. Now let's run the movie and see what happens. Okay, so this is how the power spectrum grows. Let me run this a little bit slowly. So scale invariant initially. Then the modes that enter the horizon first are the small scale modes. They are first growing only logarithmically during the radiation era. So you are seeing that part here. Note these are the modes that enter first grow first, so that's why they are bigger, but there's only a logarithmic dependence here. And now, important event in their history, matter radiation equality just happens. Okay? And now everything will start growing together as a scale factor, at least as long as it's inside the horizon. So everything here is still outside the horizon. Everything here is inside the horizon. And now you have the joy. See? So everything now grows together. Why is there a slope here? Because the mode has to enter the horizon to grow. So if it enters later, it grows less. So now we have this shape, and that's precisely the calculation we just did. It's k to the fourth and the logarithmic part. Again, just to really stress this even more, I'm now going to show you the same movie, now with p of delta, not k cubed p of delta. Remember, it's scale invariant, so you divide by k cubed, so it should start with a k cubed slope. And now, okay, so this is how the power spectrum evolves and gets to where it is today. I caution you, and again, this was already reflected in how Rogerio presented it, how Julian presented it, and I did, that things outside the horizon, how you describe the spectrum and how things evolve is gauge dependent. It depends on how you slice your space-time. So be careful. There was nothing wrong with one of the other. It's just a different way of thinking about modes outside the horizon. So just be aware of this, and it's good to learn it both ways. Okay, great. So this is the end of this review part, okay, of what you've already learned. And very quickly, yes, please.
For linear perturbation, we know that later times they kind of get linear and generated structure. I would like to know if there is a specific issue of the power spectrum for this approximation.
In this version, although this is not accurate, you want this to go above unity. Okay, so the KQ, this power spectrum, KQP, okay, not the P, but the KQP, because that's the level of how much variation there is on a certain scale. So that is the scale that is going nonlinear. Not everything doesn't go nonlinear together. Okay. So these scale will go nonlinear first, then these, then these, then these. Okay. So not everything goes. So another way of saying this is a small structure forms first, then bigger structure goes nonlinear. This is not completely accurate. I mean, and again, I have stopped. Can anybody think why I would have stopped things at roughly 0.6? There are multiple reasons. Part of it, there is nonlinearity, of course, that's important. But the other reason is that in my simple approximations, I didn't include dark energy. I was just doing matter dominated, and dark energy will slow down structure around. Yeah, this is just linear. I mean, this I literally just plotted the curve and I animated it, right? But if you include dark energy, you can. It's not hard to include. And Julian, I'm sure, can do a much more, and he will do a much more precise one. By the way, I have another question, which is a good one at this point. What do you think would happen with baryons here? So this is about in some sense, this is the dark matter power spectrum that I've done. What do you think would happen with baryons in terms of the power spectrum? How would it look different?
You have to see the power spectrum CME.
Initially, yes. But do you think its evolution would look exactly the same? When would it start looking the same? When would the shape start looking similar? Sorry? After decoupling, right? So before decoupling, baryons were sort of oscillating. They weren't able to grow. They were coupled, Julian told us today that they were tightly coupled with photons. They couldn't really grow very efficiently. So the power spectrum wouldn't have been able to grow in the baryon case up to decoupling. After decoupling, it kind of falls into the potential wells of dark matter and it grows together. So in the end, they sort of catch up, but not at the beginning. They are very different from each other. So in this time evolution, it will be different. Okay, so as I said, like you should try to do this in the notes. You will see that I've actually put in sort of pictures of hand-drawn things. I often think that, at least for me, I think I've understood something when I can draw it, when I can sketch it out. Not with the equations themselves, but when I can sketch it out. So you should try to think whether you can sketch out this shape based on your understanding. Of course, you have to solve the equations to get some understanding, but you should try to draw these out to see if you understand how this evolution goes. Okay, any questions on this before we move on? Yes, please.
Actually, the P of K is the variance of the fluctuation. This is the bracket, delta bracket.
Yes.
That is the variance. So that KQ times the P of K, what is the variance on
Logarithmics, true, yes. That's true. Sorry, I should have been more careful, yes. Yeah.
And this is clearer.
Yeah.
I agree with you. This is more clearer to see than P of K.
Right.
But on the other hand, this is not actually the variance.
I should have been more careful. Yes, it's a variance per logarithmic interval of K. It's more consistent with how I think in position space, of how much variance there is in these kinds of boxes. Okay. So at this length scale, how much variance there is. Okay, but that's a very valid point. Good. So I've told you about this power spectrum, and notice this power spectrum I put data points on there. So this is with data points. Again, Rogerio, I think, will tell you this is not so easy as it looks to put data points on there, and he'll tell you in detail how you get things there. These last brown things are from Lyman alpha forests. Again, there's a lot of detail that goes in here, and you will learn about this, but there is data on here. So all dark matter models that we come up with better be consistent that they give this sort of a curve. That's not negotiable anymore. You can't negotiate that. It's not much. There is room here now, at least in this linear spectrum. So you can imagine that data hopefully will get better, and including nonlinear scales, you can push here. So you can try to see, well, this part is already done, so all dark matter models must do this. But I can perhaps gain some information by the fact that either if I go further and I see some feature like this in the power spectrum, or the fact that I haven't seen a feature already tells me something about dark matter models. Both of those can be done. Either you can constrain the models already, or you can say you can hope that with future observations you will discover some feature that will tell you something about dark matter. So today I will tell you about a model of dark matter that will give rise to this deviation from the power spectrum on small length scales, or large K. It will turn out that this is not so uncommon. This kind of suppression of power exists in many models, but I'll give you one example and then I'll tell you how general it is. All right, so the model that I'm going to pick to discuss this suppression is that of light bosonic dark matter. Sometimes this is called fuzzy dark matter and so on. So let's just remind ourselves of what this was. So remember, I put this slide up that you all had wonderful questions about as well. We don't know the mass of dark matter. We don't know the spin. Then we discussed that, well, if it's fermionic, it cannot be too light. But if it's bosonic, it can be as light as pretty much as light as it wants. Apart from some, now we'll see that it cannot be as light as it wants, because this power spectrum tells us something. It cannot be terribly light. Okay? There is some constraint from that. So we'll get there. So we are going, just as a reminder, if it's bosonic dark matter, then the occupation number, or the number of particles in a given region, is so large that you can essentially treat this, instead of discrete point particles, you can treat it as a classical field. So that's what we are going to do. And the de Broglie scale, or the scale on which wave-like effects become important, depending on the mass that you pick, can be macroscopic or even astrophysical in size. So this is the regime that we are going to be working in. And we'll see which number for the mass can be constrained. Can we rule out some mass based on the shape of the power spectrum that we already know? So that's the goal for today. I could do this for spin 0, spin 1 particles, etc., at least in the limit that we are working with. But for starters, we're just going to start with spin 0, meaning scalar field. This has a lot of literature. This is not something new. In fact, the first lecture was something we have done over perhaps 90 years. This lecture is perhaps something we have done over the rest, maybe a decade or two. Okay? The one that's coming, or 2 days later, will probably be something we have done perhaps last 3 or 4 years. So we are getting closer to contemporary things. So QCD axioms, of course, are very old. They've been known for a while. They're an example of light dark matter where we can treat it as a field. More recently, over the past decade, people have started thinking about, past 2 decades, people have started thinking about very light dark matter, even lighter than that, 10 to the minus 20 eV. Sometimes it's called fuzzy dark matter, ultralight dark matter, etc. There have been all sorts of names. So we're going to focus on spin 0, the scalar field, and see where we get. So now is the time. Now that we're going to get into new territory, I'm going to switch to the board, and we're going to slow down and go slowly through this. Okay? This is where I'm going to. Yes. Yes, yes, please. Yes, please, please.
Why solitons are in order of GV? If they are waves, why are they not included in the range of wave dark matter?
Solid. So the question, I guess I will have to go back. Okay. I'm failing to. Right, so the question, okay, it's a very good question. So we'll close this. It's probably about this axis. That I put ultralight here, and then I said solitons and stuff over here. What I meant by this is that, of course, the dark matter, what is ultralight or not depends upon the mass of the dark matter particle. So that's what this axis is. That's what this ultralight means. But within dark matter, you can form objects that are composite objects made of a lot of particles that are solitons. And sometimes, if there are enough of them, sometimes think of those as the main particles. And you can think of those as your particles of your dark matter. It's not very easy to do that, but sometimes people do consider that a significant fraction of your dark matter is made up of composite objects, which are now solitons, or it could be even like quark nuggets, all sorts of things that people talk about. So this part is more about the composite objects. This is about the mass of the particle. Okay. Now I will try again. Let's see. Can somebody? Yes, yes.
We have some constraints on the large scales of the matter power spectrum. So the scale at which we start having freedom of exploring dark matter models that show some suppression would then be what, approximately like the 1 Humo scale, or like what?
10 megaparsec inverse. Roughly, that's where the data was sort of roughly ending. What am I doing wrong? Okay, we are back. Okay, now let's see if we can add a slide. All right. Is this okay now? Okay. So we are going to now discuss scalar dark matter, and let's just remind ourselves what dark matter needs to be. The one thing dark matter needs to be for all of the story that I've told you to go through is it has to be non-relativistic. Things can't be moving too fast. Yeah, otherwise the structure, this cold, pressureless fluid approximation, things like that break down. We want to be reasonably non-relativistic. So that's one thing we will keep in mind. Apart from that, we can model it with in a pretty general way. So let me do this for the spin 0 case, the scalar field, and I'm going to start. Hopefully this will all go through. Okay, so we are going to do spin 0 or scalar dark matter. And we're going to represent this by a field. And the field, we will call it chi of t and x. So this is a scalar field. It's a spin 0 field. Remember, spin is associated with how a field transforms under spatial rotations. So that's what spin means. Means here this is just a number at each point in space and time, a scalar number. So what is, I want to write down a model. In theorists, what do we want to do? We want to write down its action and work out its consequence. Right? So the action that we are going to consider has the following form. And Rogerio already mentioned to this how this classical field, how are we going to, you write down an action, you vary the action. You're going to see that play out right now. Okay, so here is the action for the scalar field. So what are the things that I'm writing down? This is the kinetic term. It's like when you write down a particle moving around, this is similar to the x dot squared term, but it also has gradients in it. So this is the potential term, and this is some interactions potentially with the standard model. So V of chi is not just interactions. This V of chi has two parts in it. One which is absolutely essential, that it's a massive field. It has to be massive because if it's not massive, it cannot be non-relativistic. So it better be a massive field. So there better be a mass. This m here is the mass of the field. So it has to be massive. And then it could also have some interactions, where negative lambda means attractive interactions between the particles, positive lambda means repulsive interactions. Yes? Half an hour. Half an hour left to the end. Okay. Thank you. This is what the potential looks like. And then we have, let me, what about L interaction? So that's this is often what is called self-interaction of the field. There's a mass sum and there's a self-interaction. Then interaction with the standard model, there are many things you could write down, but something for axion-like models, that's because it's, you can think of it as, I'll just write it down without getting bogged down in jargon. So it's a field that couples to the electromagnetic, so F mu nu is the electromagnetic field strength tensor. There's this field coupling to our usual photons is what this is, but there are many other things you could write down. Now for models, there are many examples of scalar fields we could think about, but one example would be axions, which, as we have discussed before, were invented to solve the strong CP problem. For those kinds of, just to give you a concrete example, this V of chi at late times can be, looks like this. This is chi. If you Taylor expand this, you will find that this is half m squared chi squared, just like we had written, minus 1/4 m squared over f squared chi to the 4th plus dot dot dot. Okay, so you Taylor expand this. This is the kind of potential that you get. Notice the lambda that we had written down is now negative, so it's an attractive type of interaction. What are these numbers m? Typically, this mass m is much smaller than an electron volt, whereas the scale f that appears is much larger than 10 to the 10 GeV. So this ratio m over f is a tiny, tiny number. It's a really tiny number. So we will, I hate to doing this because I really enjoyed these self-interactions. But we are going to set these self-interactions for our initial pass-through to 0. We're going to say that this term is too small for us to care right now. It's not always possible to do this, but for our purposes, we will do that. Similarly, this GA gamma in these types of models is proportional to 1 over f. So again, this f is a very large scale, so g is small. So again, we can, in this initial pass-through, we will ignore these couplings. So what does our model become? Our model now is much simpler. We will, for simplicity, we will ignore self-interactions and we will ignore interactions with other fields. Ignoring these interactions is killing away a huge amount of effort that is going on in detecting these things in the laboratory. So we'll come back to it later, but for our the structure formation purposes, we'll ignore it right now. And there are many effects that are interesting from both of these things. But let's just consider this action now with this master. When I wrote down this action, something else is missing from here. So this is how the field behaves. What else do we need for dark matter? What was the interaction that was helping things do what they were doing? Gravity, right? We still need gravity. Haven't really put in gravity. It's kind of there through these metric G and so on, but really I need to get the Poisson equation out of this somehow. So I have to add to this action the Einstein-Hilbert action. And the Einstein-Hilbert action is just d4x square root of minus g r over 16 pi g. Okay? So you have to add Einstein's action to this, and now we have our full thing. Okay? So now we have to just go with this and figure out what the consequences are. Things get easier from here. We've written down the model, it's turning the crank. You can find the equation of motion. We'll do all sorts of fun things. Okay. So what are the equations of motion? You vary the action. First, you vary the action with respect to the scalar field. When you do that, you get an equation of motion, which is called the Klein-Gordon equation. I don't know why it connects it, but it's okay. So this is like a wave equation, but with a mass. Okay? So this is the D'Alembert, this is the wave equation. This grad mu is including effects of the metric potentials and so on, and expansion and so on in here. And then, of course, if you vary the action, which Rogerio nicely described in the first lecture, you will find, with respect to the metric, you will get the Einstein equations, where T mu nu is the energy momentum tensor associated with this field. And if there are other things in the problem, then they will be added on to here. So that's what you get from this theory. You could analyze the effects of everything using these equations that we have. There's nothing more needed to understand how this field behaves and what's going on. But this, if you had asked me about 5-10 years ago, or 5 years ago maybe, I would have said, oh yeah, let's do this. Because I work a lot in early universe cosmology, reheating after inflation, where the relativistic fields are pretty important. Relativistic effects are important. So I try to solve this equation, try to see what goes on, and so on. But for dark matter, we have a really nice simplification that the field is non-relativistic. So you don't have to solve this full system. Plus, Newtonian gravity should roughly be okay for all things we care about for dark matter. So we don't have to deal with this full complicated mess. We can really simplify things to the level of accuracy we need for observations and get away with it. So what we are going to do is try to derive the non-relativistic versions of these equations and see what they give us. The end result will be that we will go from these Einstein equation and the Klein-Gordon equation to a system of equations called the Schrödinger-Poisson system, which will be, as it will turn out, will be much easier to solve and deal with, for good reason. So how do we get to the Schrödinger-Poisson system? Well, the first thing we are going to do is we are going to redefine the field. Remember, x is a function of space and time. I'm just doing a field redefinition, nothing meaning I'm just defining the same old field in terms of some new quantities. So just as a reminder, psi is a function of t and x, just like chi was a function of t and x. So this is a new field that I'm defining, psi. M is the mass. H bar c is 1, that's why mt is dimensionless, as it should be in any exponent. If you want, M inverse is the Compton timescale. That's a fast timescale in the problem. Next, we're going to take this definition, plug it into these equations above, along with the form of the metric that we have been considering. We're going to plug it into these equations, and we're going to simplify by doing the following. We are going to assume that the time derivative of this psi is much less than m times psi. This is an important part of the non-relativistic approximation. We are going to assume that the time derivative of the metric potential is much less than m times phi. Remember that m inverse is a fast time scale. So that's why this m is appearing. Notice we have extracted out that fast time scale here. You can think of this like a WKB approximation if you have done that before. So you extracted the fast part and you're worrying about the slow piece. What else am I going to do? Well, I want to deal with, most of the things I want to deal with are on sub-horizon scales. Notice the power spectrum and stuff, at least that we cared about, was the sub-horizon scale. So I'm also going to make an approximation that the scales of interest are sub-horizon. A way of saying this is that things like gradients, this quantity is much smaller than unity. So gradient can be replaced by a k in Fourier space. So this is what it means to be sub-horizon. We will want the field to be oscillating because only then it will behave like dark matter. That requires that h over m is much less than 1. I think I've gotten all the things that we need. So you do all of these approximations, and when you plug this definition back into the equations. Once you do that, you find, and this is a nice exercise to do yourself. It's a little bit long. If you're willing to do it quickly without worrying too much about the details, it doesn't take very long. If you're extra careful, it does take a while. And there, I can guide you to papers where it's done carefully. Yes, please. H over m. So for this to be dark matter, the field has, first of all, I'm saying that m is a fast time scale, right? So it means that the field has to be oscillating fast compared to the Hubble time. Otherwise, I can't treat this as a fast oscillating field. Okay. Only when it's oscillating does it behave like dark matter. If it's constant, it behaves like dark energy. So I need the field to be oscillating for this to work. Okay. Next, I keep on doing this. I apologize. I will get used to it by the time the last lecture comes about. So what happens when you plug that equation plug that field redefinition into the equations of motion, or the relativistic equation of motion with the approximations that I said? When you do all of that, you will find an equation for psi that looks like this. And so this is what you get from the Klein-Gordon equation. So remember, this was the Klein-Gordon equation right here. You plug this in here, and the result of that plugging everything in is that for the psi, you get this equation right here. What about Einstein's equations? You plug things into Einstein's equations as well. What happens there? The relevant piece for us is that the Einstein's equations reduce, or the most important part of them reduces to There's one important thing, because remember, we are dealing with a homogeneous and isotropic universe, so there's of course Hubble's law that comes along with it as well, which is again part of which you get from Einstein's equations. This bar means it's a spatial average. Okay? So doing this approximation reduces it to these equations. Probably doesn't seem like a much simplification to you. If you have dealt with it, maybe it does. If you haven't dealt with it, it probably doesn't. But I'll show you in a moment that when we convert it, I make some change of variables, and you will see that it looks exactly like the problem we have studied before with some small changes. Okay? So this is, can somebody, so share this system of equations. This is called the Schrodinger-Poisson system in an expanding universe. Let's try to think of this equation in a slightly simpler context. Suppose I set Hubble to 0, that is, we are in a non-expanding universe. So Hubble is 0, and the scale factor A is 1. Does anybody recognize what this first equation is? It's just it's a trick question, I guess. I keep on saying Schrodinger-Poisson. It is a Schrodinger equation. It's just a Schrodinger equation that you're familiar, single particle Schrodinger equation that you're familiar with in quantum mechanics. This phi here is your Newtonian potential. Usually in quantum mechanics, phi is some external potential in which your particle is sitting. Even though it looks like the Schrodinger equation, I urge you not to think about this as quantum mechanics. Okay? This is not single particle quantum mechanics. Psi is just describing a classical field here. It turns out that the equation is the same, but it's not. This is not quantum mechanics. What is not 0? The average? It's the average, yes. So it's the full value minus the average.
That's not quantum mechanics, I need field theory.
This is classical field theory so far. If you want, this is mean field theory, okay, at the end of the day. Let me just convince you that this cannot truly be quantum mechanics. First of all, phi is determined by psi itself, okay? So if you think about, like Ricardo did, I can write phi as the inverse Laplacian of this. If I plug it in, this becomes a non-local, non-linear equation. That's not quantum mechanics, okay? Quantum mechanics is linear. This psi star psi that appears here, it looks like the probability density that you're familiar with. It's not. It's a number density of particles. So psi star psi doesn't have the implications of probability density of particles. It has the interpretation of number density of particles. So what do you think m psi star psi is? It's just the mass density. So I urge you not, at least for my purposes, I don't like to think about this as quantum mechanics, even though the literature is full of people saying this is quantum pressure, this is wave mechanics. I wouldn't say it's quantum mechanics. Because there's no place where h bar appears by itself. There's no quantization condition. Of course, if you think about this as coming from a fundamental field theory, at the end of the day, the fact that I put out a mass introduces the h bar inside there, so it is there in the problem, so you can use it if you want, but it's not necessary. Yes? Sorry?
Maybe all of this is related to the field redefinition you have kind of introduced I into the picture, making it complex, and also this is not covariant, field redefinition wasn't covariant.
So right, so this is non-relativistic field theory, right? So it doesn't have to be, I just need Galilean invariance. I don't need it to be fully, time can be picked out, right? So it's non-relativistic now. So it's okay, like you can, and I promise you can take the solutions from here, plug it back in there, and it'll be a very good, the field redefinition will be a very good approximation to a true solution. Okay, so what, yes? Good, very good. So I've done a background split, right? I want a homogeneous and isotropic universe. I need to think about what is this. It is sourced by the average density. If I'm writing down that Hubble is sourced by the average density, I need to take it out from the gravitational potential, because remember the gravitational potential is just a deviation from Hubble. Right? It's not from the homogeneous thing. So I have to take it out. But it's good that you noted it because it's important. Otherwise, it's not consistent. Okay. So this is your Schrodinger-Poisson system. As I said, it's a field. Why do people like this? One thing you should notice is that if it was a relativistic field, it would have oscillation. You try to simulate the relativistic field. Just think about, you need to simulate m inverse or 2 pi m inverse, that's the time scale of one oscillation, and compared to the Hubble scale. The smallest mass I can think of that's consistent is about 10 to the minus 20-ish eV. Hubble is 10 to the minus 33 eV. That's a scale of 10 to the 13 in dynamical range that I would need to simulate a field over a Hubble time scale. Impossible to do. So I remember people asking me this, and I would just say, oh, this is not possible to do. Why would you even bother? But then these people did the right thing, which is, you integrate out the fast time scale, or you don't worry about it because it just comes along. It's not relevant. These equations are much easier to simulate, and that's what made a lot of this recent excitement possible, because we went to this non-relativistic system, which was easier to solve. Not to say the relativistic effects are not important. There are places where they are important. I think Diana has worked on this, where some relativistic effects, which we're ignoring, can lead to some effects on orbits of things. They've also been used, for example, in this pulsar timing array. The results that were released recently about constraining mass, those depend on some relativistic effects. They're easy to recover from here, but you can't completely ignore them. Okay. But here, let's take these equations and try to simplify them. And I don't think I will get to my promised end today, because I probably won't have time, but I'll derive the equations at least, and then we'll look at their implications next time. So here's the wonderful magic that's going to happen next. So we look at these equations right here. And it seems like I keep on doing field redefinitions, but this is part of the game, right? You try to simplify, things are complicated, you simplify it by appropriate choice, either of coordinates or definitions of things, till it becomes solvable, or till you map it more appropriately. You redefine things till it maps onto a problem that has already been solved before. That's the best way of doing things. So one way in which it becomes close to what we have solved before is that you do a following definition. By the way, I forgot to say it before, but I should write it down somewhere. Rho is m psi star psi. Okay, that's the mass density. And you'll see that I'm using that in this definition. So psi is a complex field. Does anybody when we started with the Klein-Gordon equation, you had to specify two initial conditions, right? You had to specify the field and its time derivative initially, because it's a second order differential equation. I've just converted it into a first order differential equation. What happened? Did I lose something along the way? The key is that psi is complex, whereas chi that we started was a real valued field. So psi still has two parts to it. It looks like, yes, this looks like the probability amplitude, right? But that has a phase. It is because the equation is the same, so you can think about it that way. Sorry, I didn't write the second part, but it's a complex field. So there is a phase that is also there in this system. The number of initial conditions that you have to specify is still the same, two real variables. So this is the field redefinition that we are going to make. Rho you should think about as the mass density. What is the theta is a phase, but we are going to make one definition which will make everything work out in the way that I want. I will define a velocity as a gradient of this phase. There's a small velocity that I'm defining as a gradient of this phase. You now plug this into the Schrodinger-Poisson system, and the equations we get for rho and v are the following. Do you recognize this equation? This was the mass conservation equation we started with. Same equation again. Great. Okay. So we know how to deal with this equation. This is very nice. What about, and this is, I have made no approximations from going from Schrodinger-Poisson equation to this equation. Just definition. Yes. The next bit, what do you expect should come next? What equation do you expect to come out of here? Some equation for v, right? Because v is a variable for theta of v. Exactly, right? So the next equation that comes about when you plug this into the system is 1 over a here is the same equation as before that we had, but this is not all. Okay? There is because I told you there will be deviations in this model, right? So there is a correction, and that correction can be written in the following way, where Q is defined as Laplacian of square root of rho divided by square root of rho. To make the units come out right, I have to do this. Okay. So Q, this gradient of Q is an extra term that appears in this Schrodinger-Poisson system, which did not appear in this pressureless dust that we were considering earlier, or this term, if you look at the stress energy tensor, it's like a stress. Sometimes people call it the pressure or quantum pressure. Yes? 5 minutes. Okay, great. So I got worried that he was disagreeing with me. Okay, so you get the same equation, but just one extra term. Okay, yes?
This parameterization is very similar to the Broglie-Bones interpretation.
The what, sorry?
The Broglie-Bones interpretation.
The what bond? Sorry, I can't. The Born interpretation. Okay. I think because the equations are the same, right? So you can't. Mathematically, everything will look exactly the same. That's not surprising. Well, it's not a coincidence because, of course, when Schrodinger wrote down his equation, he was looking at E equals P squared over 2m, which is a non-relativistic relation. And that's how he wrote down the equation, right? So it's not a coincidence that non-relativistic quantum mechanics is coming around in a similar way. We went from a relativistic equation to here. So the fact that equations come out to be similar is not surprising. Yes. Yes.
When you introduce that rule,
Yes.
it's just a classification, but if we integrate volume, universe, we obtain a relation between the integral of rho and m on the other side. If we normalize the field, apparently the integral of rho would coincide with the total mass.
Yeah, absolutely. Yes.
there is some motivation to normalize fields or not, because it's not a probability.
You can, but I prefer to think you can normalize it, and sometimes people do. But I like to think, because I want to write down equations where this is a mass density, right? It makes more sense to write it this way. So the integral of psi star psi over all space, as you were suggesting, is just the number of particles, right? And m times that is just a mass.
Yeah.
Okay, so it is that, and it's not. There's no further need, because it's exactly doing what you want it to do. So the integral of psi star psi is just the total number of particles. Another interesting thing here is that because in a relativistic field theory, you would have expected the number of particles not to be conserved. It's a real field, there's no conserved charge here. But when you do the non-relativistic approximation, you are at such energies that you no longer can change the number of particles. So effectively, in the non-relativistic theory, the particle number is conserved. Okay? So that's why this number, and we'll write down all the conserved quantities next time. Let me just finish here very quickly by writing down the final equation so that we have it all ready for next time. The final equation that we get, this one shouldn't be surprising, of course. This I don't have to do anything. This is just the same equation as before. If you want, this is rho minus rho bar. So this equation is exactly the same as before. This equation is almost the same, except for this extra term. This term is important. That's where the effect is going to come from, the suppression effect, because otherwise it would be the same thing. And this bit right here is the equation we already had, the mass conservation equation. Remember, the d by dt here is always thought of as a convective derivative. That is, d by dt is equal to partial plus v dot grad over a. That's how you should think about it. So these then are now we have reduced the problem of a non-relativistic scalar field to things we've already almost dealt with, okay, which is just fluid equations, mass conservation, momentum conservation with an extra piece, okay, and Poisson equation, which was already there. And now we have to analyze this to see what effect does this term, for example, have on the system, this extra bit. Okay. Notice this term comes with a lot of gradients. It comes with a lot of gradients in there. So it's something to do with the fact that the field is, you should expect the effects to be important when the gradients are important. And gradients are important on small scales, right? We're taking gradients on small scales. So the effect should be more prevalent on small scales than large. And that's what we are going to see will be the effect of this term. There are other subtleties in here that we will discuss, but I think for the moment, this is a good stopping point. I'm going to linearize the equations, and I'm going to derive an equation very similar to what Rogerio had derived in his lectures and what we showed today, with some small deviations, and see what that does to the system. Okay, Merdad, good time? Okay, thanks. Yes.
So I was wondering, at the beginning of your lecture, you mentioned the values of the mass and F. And I understand in mass you will consider light particles, but the values of F.
I think that's, yeah. So that's the values of F, like 10 to the 12 GeV for some of these cases. For QCD, that's roughly the range that is used. So that's what I use. Usually this scale is very large, sometimes even taken to be M Planck. It's a model-dependent statement, of course. The reason that scale, at least in this type of models I was writing down, if it's not too large, then your interactions are too strong, and it would not be good dark matter anyway, with other things. So it all comes together. But if you're just thinking of a scalar field, you're free to write down what potential you want. Depends on how serious you want to be with connecting it with some high energy completion or something like that. So here, for example, this ultralight, forget what this ultralight business that was done. For them, the F was about 10 to the 17 GeV. That's what they roughly picked the number to be, and m was 10 to the minus 20, 22 eV. So this ratio is just ridiculously small. That turned out, as we will see, that you can, with that kind of potential, the F and the M work together to give you you have to choose them appropriately so you get the right amount of dark matter today. They're not completely free. So you need some, so for example, for 10 to the 17 GeV, you needed M of 10 to the minus 22. But we'll write down an equation and you'll see what the relationship between them is. But it's not necessary, I mean, again, this was a model specific thing. You could just have started with saying, I just have an M squared phi squared model. I don't care about the lambda that comes here. It couples to nothing else. It's just, or you can say it's all gravitationally coupled, which means all couplings come with an 1 over m Planck. So they're too small to worry about in most cases. Yes?
Yeah, my question. What goes wrong if I, instead of this, assume like a fluid or particle or shell that's having mass of just a particle instead of this?
I think you can still do that. There is in some sense you will, so one thing you will lose, oh, sorry, good. The question is, what would go wrong if you just did particles with the same mass without thinking about this description? You would, I think you could do that. You would, for example, lose, if you're thinking of, you would lose this term. Okay. This term would not be there in your system. So you would lose, you would just get pressureless just that you were thinking about. It's sort of an incoherent collection of particles that you'd be imagining. So you would lose that term, at least, yeah, I think so. So it's related to gradients of the field. Right? I guess maybe I'm not answering the question correctly. So if here I'm assuming some sort of, these things are in some coherent configurations, right? Meaning there's a field there. What you are suggesting is just something completely incoherent, that there's no coherence in the field. So if there's no coherence in the field, I don't know how to think about these gradients very well, at least. So I can't think of how this term would come about in that case. But I think the right description, in my view, if you have such a high, if I'm thinking of in terms of fundamental particles, if you have such a high occupation number, this has to be a good description of the field, unless you're saying something about the initial conditions where there's no coherence in the field whatsoever. But it's a subtle, I must admit, like I worry about this, and I don't have a very clean answer, to be honest. Right? It's probably correct, but if you ask me more and more details, I would get myself into trouble about what's going on in the system. Yes, please.
So your two parameters are mass and the initial condition.
Yes, that's it. For the moment, the initial field configuration that you start with, and the parameter in the Lagrangian is the mass. Then there's just the initial field configuration. And there are two, I think maybe you're asking, so there are two, you have to specify the initial condition for rho and for v, or rho and theta. Right? So there are two free functions that you have to specify. Just like you would have to, if you had a real field, you would have to specify the field and its field derivative. I've just replaced that by a complex field, so now it's a real and imaginary part that has to specify. By the way, you should tell me if this, for some of you, this might be very familiar. Some of you, it might get too technical. But give me some feedback so I'll know how to improve next time. So just let me know, and we can adjust things. Next time onwards, it will, the formal things are gone to some extent. Right? We are now going to look at implications, and it'll look very similar because we've gotten things we understand. We'll again pick up after the next lecture. We'll do again some formal things and then look at implications.